All right, hello and welcome to the last lecture. So today, finally, we're going to define what the Fukaya category is. We're in a good position to do that, and we're going to have a closer look at the Fukaya category of homogeneous surfaces. Okay, so let me recall. So where did the Fukaya category appear? It appeared in the homological mirror symmetry conjecture, which says that there's a pair of manifolds that are dual or mirror to each other in some sense, such that there's an equivalence between categories so the derived Fukaya category of one is equivalent to the derived category of coherent sheaves on the other, and vice versa. So you have the A side on, so that's what you call the A side or the A model, and that's what you call the B side, the B model. So the A side on the dual is equivalent to the B model of the space X. Okay, so we know now how to make sense of the term equivalence between categories. Moreover, we know what the D stands for, some sort of categorical localization, taking a quotient, making a quotient out of a category, and that's the derived category. So what we don't know is this thing over here. So the homological mirror symmetry has been established for a bunch of examples. So I can give you very quickly in words something about, let's say, the elliptic curve, but maybe later on, just to say what this encodes and what this encodes, and you know how there's a mirror map between them that sends things on the left to things on the right, and so on and so forth. Okay. So I'm going to give you the definition of the Fukaya category, but before that, of course, I need to tell you some references. So the first one is called Beginner's Introduction to Fukaya Categories. It's a very nice set of notes written by Duni Oru, who's an expert of the field, and he poses this to be like a prelude to this very, very rigorous, detailed account of Fukaya categories and Picard-Lifshitz theory by, of course, another expert, Paul Seidel. If you want to dive deeper into the subject, of course, you should start with these notes and then eventually have a look at the book. Okay. Yeah, so I need to make some definitions before we come to the actual definition, the Fukaya category in general, and then of course that's going to be a version of, we're not going to give it in full generality, but a version of it, and then we're going to narrow it down to the case of surfaces. Okay, so exactly say what the objects are, morphisms, and blah blah. Okay, so recall, for a symplectic manifold, there's a way to define the floor chain complexes. This is what they look like. So we're using the intersection variant. So here, this complex had a differential defined on it. Let me call that differential M1, or okay, let me just still call it D. We called it D in the last lecture. And here, each CFI are generated by intersection points of Lagrangians, yeah? L0, L1. So in short, it's generated by the intersection of L0 and L1 such that the index of those points equals I. Okay, that's the ith graded piece in this complex, And then we said that you have a differential that goes from CFI to CFI plus 1, which counts J holomorphic curves from, let's say, so it goes from P to Q. In fact, all curves from P to all candidate points from P to, let's say, output Q with a coefficient. Okay, so there's a coefficient here, and so it counts all. So what this looks like is something like this. So you have a point P here, the intersection between L0 and L1, and you end up counting these oriented maps, J holomorphic maps, from the disk to, so let's say you take the upper half of the disk. Sorry, I should draw it like this. So you have this 1 and -1, let's say. So the 1 gets mapped here, the -1 gets mapped here, and this part of the disk gets mapped to this part of the Lagrangian, and this gets mapped to this. So you remember, this is what we called a J holomorphic disk with Lagrangian boundary condition. Okay, so the differential basically counts just that. And so there's a way that you could define cohomology of this complex, after showing, of course, that this d squares to 0. And so you're able to say what HF star is after saying what CF star is. And so reminiscent of the product in cohomology theory as usual, we can define a product or a composition. Let's call it M2 from at the chain level. So it goes from CF L1 L2 cross CF L0 L1 to CF L0 L2. Okay, so it takes as inputs an intersection point here. Let me call that 1, 2. An intersection point here, let me call that 0, 1, and gives you as output an intersection point between 0 and 2. So let's call it 0, 2 or 2, 0, whatever. So let's call it 0, 2. Okay. So now you see here the definition of the differential said that as input it takes an intersection point between L1, L0 and L1, and as output it again takes an intersection point between L0 and L1, and there is you count the number of disks. Those are the gradient trajectories in the floor picture. Okay, so you count these disks. So what you're counting here is really, you have L0, L1, L2, 3 Lagrangians which intersect at points. So you have P01, P12, and you have P02. Okay. So what you end up counting are these holomorphic triangles. Okay, so if you can call these bigons, because they just have 2 sides and 2 corners, vertices, you can call these triangles, J holomorphic triangles, and that's what M2 counts. Okay, so so these are U with some way to have mark points on the boundary of the disk. It's a map from D to your space M, where this part, let's say, so this part gets mapped to, So let's call this Z0, Z1, Z2. So this part between Z0 and Z1 gets mapped here. The part between Z1 and Z2 gets mapped here. And the part between Z2 and Z0 gets mapped here. Okay. All right. So this is a pseudo holomorphic disk contributing to the count M2. Okay, so it's a way to connect these two input points right over here to this output. Okay, that's what we're doing over here. So now let's consider M. So when I write this M, you should really think of this space of all such maps all together. So M that goes from, so for simplicity, let me just call this P1, let me just call this P2, and let's call this output Q. So I'm going from, let's say, P1, P2 to Q. Okay, so you have P1, P2, and Q. Well, in the previous notation, I was writing the output first, so you could still do that. Let's do that. So Q, P1, P2, and here you have the class of this disk and almost complex structure J. So this is how we denoted it earlier. So the class was denoted by A, and the almost complex structure. So that's how we denoted it yesterday. Okay. So be the space of J holomorphic maps, okay, with some condition on them of finiteness. And so the expected dimension, so what was assuming transversality, you remember this component of defining floor homology, we had 3 steps: transversality, compactness, and boundary. Okay, so assuming transversality holds, we knew that we have this set of all disks, or this modular space is the right expected dimension. Okay, so the expected dimension of this M is given by the Maslov index. So I mentioned this yesterday. So which means that which is basically, so because it counts disk, right, so to M2, so this M2 counts such disks, and to be able to count, we want this to be of 0 dimension, right, compact and 0 dimensional. So you start with this set as usual. You want this set to have a dimension, so you want it to be eventually, after compactification, you want it eventually to be compact of 0 dimension, so you can count it. Okay, so the count is finite and meaningful, and so M2 is defined, however it is defined. So we want the index of U to be exactly index of, or the degree or Maslov index of this intersection. Let's say degree of Q minus degree of P1 minus degree of P2. So this should ring a bell. You remember I told you that the index of a bygone J holomorphic disk between P and Q is 1. Yeah, it starts from a point, it's between a point of some degree going to a point of degree 1 more. Okay, and then we had to quotient by reparameterization to bring it down to 0, eventually compactify it so that the count becomes finite. So there we had index of this disk was +1. So this meant that the degree of Q minus degree of P has to be +1. So that's exactly what we're saying in the case of triangles. So the index of each such triangle or such a map has to be, the Maslov index has to be degree of the output minus degree of the inputs. Okay, minus degree of sum of inputs. So it's something that's similar. Okay, so this is of course assuming transversality holds. All right, so the definition of M2 is the following. M2 maps P2, P1 to the product of P2, P1, which means you sum over all outputs and you weight it by the number of elements in this M, okay, such that those elements, so for all u in M, the index of u equals 0. Okay, so M2 counts J holomorphic triangles of Maslov index 0. Okay. So it's a product. So under more assumptions, the Leibniz rule holds. So you get a product. If you take the differential of the product, you'll get how do you say? Right, so if you take M1 of, you compose it with M2, you'll get, let's say, plus or minus M2 with M1 applied to one argument and the other one, and then plus or minus M2 applied to with P and M1 applied to the other one. Okay, it's the usual way in calculus. Okay, so you have the Leibniz rule holds. So it doesn't hold for free. So we need more assumptions that I don't want to say, but just to say this is highly technical. It doesn't just come for free. Okay, so but so this M2 is not associative. What does that mean? That means if I extend this product to, so M2 of, I don't know, so let me just say it like this. So M2 of, let's say P, so you have 3 points coming together, let's say P1, P2, P3 is not necessarily equal to M2 of P1, P2, P3. Okay, that's what associativity means. So if you have 3 points, 3 inputs, and then if you take a product of 2 of them in different order, the answer does not necessarily have to match. So this is not associative. However, M2 you can induces an M2 at the level of floor cohomology, you remember. So you have something at the chain level, but then you can also take the cohomology of that chain complex, cochain complex, and you get the cohomology. So at the level of cohomology, it gives a map which is associative. But of course, if you're familiar with homology, you know that you have information that gets killed or is lost when you go down from the chain level to the cohomology. Okay. All right. So what do I want to say next? So this problem that it's not associative is only solved up to a homotopy using higher compositions. So that's one composition, but you can do higher compositions, which are also sometimes called higher products, that satisfy a relation, and you'll see what I mean, that it's associative up to something. So let's define MK, higher compositions. So this time you'll take k inputs and you'll get k plus 1th output. Okay, so M2 took 2 inputs and gave a 3rd output. So you take Lagrangians first of all, and you define Mk to be this k minus 1 Lk blah blah going up to L1 L2 times Cf L0 L1, and finally the output lives in L0 Lk. Okay, so this is of degree 2 minus k in the situation when so when the complexes are graded. So let me just leave that for now. We'll do that discussion later on. And this counts pseudo holomorphic k plus 1 gons. This shouldn't be a surprise for you, because as I said, it takes k inputs and gives you another output. So you have k plus 1 vertices, and you have these disks that are maps from. So we've seen this picture before when I defined J holomorphic disks with Lagrangian boundary condition. So I made this picture. So you have these intersection points being mapped here, and these arcs on the boundary of the disk being mapped to the associated Lagrangian. Okay. So you remember, for transversality to hold, sometimes we need to perturb some equations, some maps, also some Lagrangian, to make things consistent, and so that everything is good and we can eventually count what we wanted to count. Okay, so these are the k plus 1 gons we're talking about, and so we can define in a similar way. So taking an output, let's call that Q, points P1, Pk are the inputs, that's the class of the disk, and the almost complex structure J. Okay, so it's the space of k plus 1 gons, which are holomorphic disks, which represent this class. Okay, so okay, so now the usual you quotient by reparameterization action by automorphisms of the disk. Yes, these are parameterized by the disk, right? So you you quotient them by the reparameterization action of automorphisms of the disk. So something that's or in other words, you could also, if you don't want to take the quotient, you could also just fix the 3 points and just track the images of the other ones, and that should also give you what you're looking for. So for a fixed conformal structure, this index is again given by the Maslov index, and so the expected dimension, assuming again that transversality holds and everything is okay, of this should be that k plus 1 minus 3, which is k minus 2 plus the index of the disk U, and that's basically just k minus 2, the same, plus degree of Q minus the sum of degrees of the pi. I goes from 1 to k. Okay. So this means that so if you consider all disks of the right index, then this expected dimension comes down to 0, and after compactness step, you should be able to count. Okay, so mk is defined to be the sum of number of these p1 pk times the output q. Okay, so where this u, of course, very important to write. So the u, the representative, has index. So this q belongs to, first of all, the disk, and it's a point on the disk, and this index is equal to 2 minus k. Yeah, so that the sum becomes 0. Okay. So this is, maybe I should say, up to choices. Okay, it doesn't just naturally fall into place. We need to make some choices, you know, so that transversality holds, choices related to the conformal structure on D2, and of course introducing domain dependent almost complex structures, and so on and so forth. Also some choice of Hamiltonians, a family of Hamiltonians, and perturbation using Hamiltonians. So everything is consistent. Okay. So assuming that we have this condition with your symplectic form and pi2 of relative homotopy group for all Lagrangians. So this is for all I. The products Mk, they satisfy I'm not going to dwell too much on this, but maybe just write it down for the sake of reference. So it's going to take how many? This plus 1 arguments. No, exactly this many arguments. Okay, so here you'll write this many arguments. It's M sub something, and inside here you have another M, which is going to take L arguments inside. Okay, so in total you have K plus 1 minus L arguments. Okay, and this sum comes out to be 0. So there is some sign here and a meaningful summation. So let's forget about this and let's just try and write it down. So maybe I should just write this goes from 1 to K, and this J, sorry, where's the J? Yeah, there's a J. So let's forget about the J, but there's another index in those intersection points which goes from 0 to K minus L. Never mind. So for K equals 1, what does this mean? For K equals 1, this means that you have the only possibility for L is 1. Okay, so you only have an M1 appearing inside. And when L is 1, this thing becomes 0 and you only have an M1 outside too. Okay, so what this, scary equation comes down to is, okay, and M1, what is M1 according to our definition? If you have M1, then you need only L0 and L1, yeah, and that's precisely the differential. Okay, so what this A infinity relation, so this is called the A infinity relation. What this boils down to is that the differential squares to 0. Okay, fine. Let's put K equals to 2. You'll have to believe me, or maybe just look at this, just these indices. Okay, you don't have to plug in any or maybe just hit and try for a couple of minutes and you'll figure out. So K equals 2 is the Leibniz rule. So K equals 2 means L goes from 1 to 2. Okay, so when L is 1 or when L is 2, let's say, you have M1 composed with M2 plus or minus, that's a sign involved, and when L is equal to 1, you'll have two of them, M2 with let's say M1 appearing here and 1 dot something else, plus or minus M2 of the dot, M1 of the other argument, and it's equal to 0. All right, that's the Leibniz rule. And now we look at K equals 3. So maybe I can erase this now. So K equals 3 is saying that your L goes from 1, 2 up to 3. Okay, so when it is okay, so now you need to do a little bit of work. So maybe I can just write this down for you. So you get plus or minus M2 composed with M2 because because K is 3, so now you have 3 arguments involved, so you have 3 dots, fill it in with whatever, M2 of M2 and a dot plus or minus or maybe, okay, plus or minus M3 or maybe M1 of M3 plus or minus M3 of M1, and then M1 could be in two other places. And finally, and you put it equal to 0. Okay. So for the moment, let me try and take everything like over here to the other side, to the right hand side, which means that I can get rid of the 0, turn this into an equality sign, and maybe change signs, whatever they may be. Okay. So what do you see? You see that if the right hand side of this equation is 0, this means that M2 is associative. Yes? And if the, sorry, am I? Yeah, that's right. Right. So you know that this is associative, and just I just need to quickly see something. Yeah, okay. Oh, sorry, I should say left hand side is 0. So let's say the left hand side is 0. This means that this thing is equal to 0. You get that M is associative, okay? And if I put this thing equal to 0, this means that M3 is a chain map, okay? That just always means it commutes with the differential of your complex. Okay, so you see when I take M1 of M3, it should equal, because M3 has 3 arguments, so there are going to be 3 possibilities of M3 composed with M1. Okay, so that shows that it's a chain map. So you see M2 is associative to up to a higher composition, a homotopy, which is compatible with the previous maps. Okay, so that's what the, and all of this, of course you could continue, all of this is packed in one magnificent equation, a scary one though, but if you just unpack it for, let's say 3, you're at peace with it in this infinity relation. Okay, so now finally we can define what the Fukaya category is. And that's a version so M is your symplectic manifold, then Fukaya category of M, that's how you denote it, is defined as follows. It's a long definition, but we've done a lot of hard work to reach this definition. So the objects of this, it's a category, right? So its objects are Lagrangian submanifolds, I should say, very important, suitable Lagrangian manifolds. So that slips a lot of technical stuff under the rug. Again, I should remind you, there were a lot of choices that are made along the way, and so this kind of puts some extra conditions on the Lagrangians so that you can either reduce the number of choices you make or that everything falls in place. Okay, but if as a first impression, you should just imagine that the objects are Lagrangian submanifolds of M. Okay, and the morphisms are floor complexes CF between with the floor differential. So now that we've been introduced to these higher products, so the first one in that sequence is the differential, so I started denoting it instead of the D with an M1, okay? And then we have, there exists a composition or product of morphisms given by M2 okay, which is only associative up to homotopy given by higher products. That's what it means exactly, and it admits a sequence of higher products or compositions MK which satisfy the A infinity relation. That boxed one I have there in orange. Okay. Okay. So okay. So the floor chain level details involve choices. We've already said that, but at the cohomological level, the Fukaya categories that come out for different choices are equivalent. At the level of so they're quasi-equivalent, which means at the level of cohomology, you have an actual isomorphism between the two Fukaya categories defined for different choices you make. Okay, so there's one small remark I want to make, is this very important assumption that we were making in defining all these higher compositions was assuming that transversality holds. Okay, so your chain complexes, all of them, are generated by intersections between transversally intersecting Lagrangian submanifolds, okay, always. So the problem is that this is, so let's say first let me say such a category which has these higher products that satisfy the infinity relation is called an A infinity category. Okay, we postpone the definition of this. That's a definition. So the Fukaya category is an A infinity free category. Now, what does that mean? that means it's just to distinguish it from a category that's not an honest infinity category. With that we mean that you cannot talk about units, complexes between, let's say, L with itself. That's a problem because L does not intersect itself transversely. However, if I perturb this, I move it along a flow of the Hamiltonian vector field. So if I move it along some flow, so I've perturbed it a little bit. You remember this picture of the zero section, and I said that so this with itself is not transversal, but you could move it a bit and now it becomes transversely intersecting. So you could do that, but essentially you cannot talk about such units, such morphisms between a Lagrangian and itself. Okay, so which is why we need to add this prefix here. So this is not possible. I need to add the prefix pre here. Okay. All right. So, but if we do consider, if we decide to descend to cohomology, then we can speak of units, but then that's a different category. You call it the Donaldson-Fukaya category and not the Fukaya category. Okay, but that's so let's just leave it at that. So maybe we can have a break of about 5 minutes or maybe 6-7 minutes, and then we can resume. Okay, so let's talk about Fukaya. So this is topological Fukaya. Let's say this in a bit, what this means. Of surfaces of genus higher than 2 or higher than 2 or greater than 1. So this means I'm talking about, we've been classified by genus, so I'm talking about surfaces, closed oriented surfaces of genus 2 or 3 or more. Okay. So so first of all, this sigma, which is of genus G, and that G is now throughout the remainder of this lecture going to be greater than or equal to 2, is it's a Riemann surface. So we know about Riemann surfaces. It's a symplectic manifold with symplectic form given by the area form. Yeah. So you could do this whole story in, the usual way. Of course, keeping track of these areas. So the symplectic form plays a role in everything you do. But you could also, so in the count of those disks, there's an area that you need to keep track of. Okay, so in that finiteness, you need to somehow normalize the effect of counting areas by inserting a certain parameter which keeps track of those. Okay, so it sort of goes in the reverse direction. So the effect of area being incorporated cancel out, and so you have some sort of finiteness. So, but what we're doing in the topological model is that we come back down to earth and we disregard the area form. Okay, this is joint work with Christian Blanchet. But before this, maybe I should mention that in the symplectic situation, it's the same surface. If you consider it with the symplectic form, then any curve on sigma is Lagrangian. So curve is one dimensional. It's half of the dimension of the Riemann surface, okay, and it's maximal isotropic. You remember, it's isotropic because if I take at any point, I take the tangent space. This is what the tangent space looks like. Which is spanned by a single direction. Yes, a single vector. And so when you plug in any vector on this line, when you plug in to your symplectic form, so let's take uv, and uv are, you know, in the same space, you get, because this is skew symmetric, you know, you can pull out, and bilinear, you can pull out the coefficients, the scalar coefficients, and what you get eventually is W, I don't know, let's call that spanning vector alpha, 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 which is 0, then some coefficient here, doesn't matter, okay. So all curves on a surface are by default Lagrangians, okay. So when we look at the topological model, we're actually mimicking the symplectic picture, the picture that I drew, you know, in steps in the previous part of today's lecture, but we're disregarding the area form. So basic objects for us are closed curves on the surface. These are immersed curves. So this is less than being embedded. So we want to just expand on the, so we want to incorporate immersed curves as well. So this is less than being embedded. So for embedding, you want it to be a diffeomorphism onto the image. So, but these are just immersed. So closed immersed curves on sigma and with marked points. Of course, this is some data that you should not pay attention to for the moment, or maybe not at all for this lecture. And then what more? Which are unobstructed. So in this really nice, easy example of the surface, I can tell you, unpack this for you. I can tell you what this means exactly. But if you remember, when I was writing down objects of the Fukaya category definition in general, I said that they're suitable Lagrangians. Okay, so that's suitable Lagrangian, so that the differential squares to 0. Okay, so you actually have the floor chain complexes, the morphisms that you're going to define are genuinely chain complexes. Okay, so these are unobstructed. So this means that it's an immersion, which is, so you have, so gamma is an immersion, which is unobstructed. Oh, sorry, I should say not null homotopic, and does not bound an immersed fishtail. What does that mean? This is what a fishtail looks like. Okay, so you don't have such a thing, such a kink in your curve. All right, that's what unobstructed means. So this is an obstruction for, for the differential squaring to 0. Okay, that's the problem. So there along the way there are lots of obstructions that you keep adding hypotheses, so suitable hypotheses, so that you kind of clear these obstructions and you finally eventually you're able to give a model. Okay. All right. So there is a by the way, there's a symplectic story which comes before us. It's the actual Fukaya category, not the topological model. The Fukaya category of surfaces, which is there in the work of Muhammad Abu Zaid, that I must mention. So there's a floor homology theory for immersed curves, just like embedded ones, that we need not repeat. So you do the same things over again, which is that you consider Lagrangian floor theory. So the complex is every graded component in the complex is generated by intersection points of those Lagrangians. Between those intersection points, you count the J holomorphic disks. Those are the gradient trajectories in the floor context, and that's how the differential is defined, and then the differential squares to 0, blah blah. So all of this stands, but what we have is what we need. So I told you that the symplectic form somehow keeps track of the area, okay? And if you suppress or disregard the symplectic form, which we are doing in this topological model, we're not considering the surface anymore as a symplectic manifold, but like just a topological manifold, then we need some additional assumption so that we can obtain finiteness eventually. Okay, so we need what is called the admissibility condition. So this is inspired from the admissibility condition or weak admissibility in the context of Higard floor theory, which is a close cousin of floor theory, but in a different context. So the condition is the following. So gamma 1, gamma 2, these are two curves, is an admissible pair if any Euler 2 chain has, or Euler 0 2 chain has positive and negative coefficients. Okay, so this is just a fancy way of saying the following thing. So if you take two curves that intersect, so you see two intersections between these two curves, and between the curves you see two regions. There is this region, and then there is this blue region that continues at the back and then finally comes up here. Okay, so you see two regions. So these two regions, the linear combinations of these two regions is what you call a 2 chain. Okay, it's a 2 chain means a 2-dimensional chain. So it's a 2-dimensional regions, and they form a 2 chain. So a formal linear combination of them is what you call a 2 chain. And Euler 0 means that their Euler measure is 0. So this Euler measure is in some sense a generalization of what is the Euler characteristic that you would be familiar with. And what this really means is that all we require is that one comes with a positive coefficient and then the other one comes with a negative coefficient. So if this one is negative, then the other one is positive, and so on. Okay, so for example, so I'm going to give you some examples. Any two homologous curves are admissible. So if you look at these two curves, this is an example of two homologous curves. These are two curves that have the same homology class. Okay, so these two curves are admissible because the two chain that comes up is has positive and negative coefficients. Two any two curves bounding a subsurface so let me draw a picture. So you can play around with curves as much as you like because this is something that's manageable. Okay, so let me draw some curves here and then let's try and make sense of what I've been writing so far. So one example would be of this thing here. This you've already seen. That's the case of two homologous curves that give you a chain with positive and negative coefficients. Okay, and it continues at the back. So let's say we have something like this. So this blue thing is that dotted strip at the back also, and this has, let me do that with red, positive and negative coefficients. We could take a curve here and of course another curve here. And here you see that you have two intersection points. And you have a region here and you have a region here. Yes, so let me shade this with an orange, the remainder of this and this dotted region at the back that goes around. And you have something over here. So you have, let's say, a positive and a negative coefficient here as well. Okay. But what this admissibility really blocks out or forbids is something of this sort. Two curves that bound a cylinder. So now you only see one region between them. It's a band that goes around this handle and it has only one sign. Okay, so it's not positive and negative, it could be just positive or just negative, whatever. And so this is not admissible. Okay, what is not admissible? This pair, gamma 1, gamma 2, is forbidden. Okay, so you don't want curves to bound cylinders. This is something that obstructs or eventually leads to something which is not finite. Okay. All right, so let's see. So we have two curves. They could intersect in points. Yeah. If you have two admissible curves, of course, we need admissibility. So we're going to define floor homology for floor complex for an admissible pair. So this is an admissible pair. So that's our standing assumption throughout. Okay. So now you may ask that, can you always find admissible pairs? There's a way of moving or transforming a pair of curves that are not admissible, transforming them into an admissible pair. So you see, you could make a finger move on one of these, which is an isotopy like this, to create these two essential intersection points. So you're able to do that. So which means that if isotopies are, everything is defined up to isotopy. You remember we said that the floor homology is also invariant under some sort of isotopy. In that context, is Hamiltonian, and of course other choices. So this is a version. The topological version will also be invariant, but of course you can't get rid of this. These are essential. Okay, is what I want. So it's a very generic condition to put on your very harmless generic condition to put, is that you start with an admissible pair. Okay, so now I need to give you the degree. Okay, so let's say CF between these is generated by intersection points. That's no news, we know that already. So in this context, the topological context should be the same. But I need to give you some meaning of the degree of intersection point in this case. Okay, so the degree of intersection point is the usual Maslov degree, but we're just looking at Z2 graded complexes. Okay, which means that which can be of degree 0 or degree 1. So this means that the degree of intersection point is induced by orientations or the sign of intersection. What does that mean exactly? Is this. So we make this convention. If this is how your intersection point comes about, you say that it is degree 0, okay, or it's even degree, 0 mod 2, or it has even degree. Okay, and if your intersection point comes about like this, then so these are two Lagrangians which are oriented. Inside this oriented, they inherit this orientation where it is oriented. Okay, I don't have my sigma here, but initially I wrote. So they come about like this. So this is 1 mod 2 odd degree intersection points. Okay, so you have like a 2 periodic thing over here. So the sum of CFI gamma 1 gamma 2. Okay, so the only possibility is for I is 0 or 1. All right, simple. And now we define bigons. So U from D to sigma, which is a bigon in the usual way. So you have this half disk being mapped to gamma 1 gamma 2. So that's the intersection points, and there's an orientation on the, so you have something like this. Okay, or whatever. Oh, this, maybe we don't need a rotation over here, but anyways, so this part goes there, the other part goes here, and so on. Okay, so it's the same thing, and well, similar thing. So the differential, so by the Riemann mapping theorem, each such disk has a unique holomorphic representative. So we're going to define the modular space of all such bigons between P and Q to be the following. So D from CFI to CFI plus 1 is defined by sending P to a sum of outputs Q with a sign. So Q is in U and U is inside this modular space QP. Okay, so this has a similar definition, just that you see it no longer has a dependence on an almost complex structure. Okay, because this is just a topological model. All right, so it counts bigons, and yeah, let's what it is. So the sign is, well, it has, we have marked points here, so it +1 for marked each marked point, and another +1 if the boundary of gamma 2, if let's say the orientation of gamma 2 does not coincide with its orientation as boundary of U. Okay. So what does that mean? That just means that, for instance, in this point here, this gamma 2, the orientation of gamma 2 does not correspond to its orientation as boundary of this disk. Okay, if it did, then it should have been oriented in this direction. Okay, so in this case, for this such a bigone, you will add a +1. Okay, so it contributes to the sign. Anyways, okay, so we can check that d2 squares to 0, and the way to do it is just, you know, you play around with signs. So everything is mod 2, everything depends on the orientation, and you just check signs and you see that the signs eventually cancel out. So if you have, so d2 is what? You go from, let's say, P to Q, and then Q to R, apply D twice. Okay. So when you have this jump, you remember you always have a jump of 2, index 2, whenever you want to show the boundary part of the definition. So you'll have something of this sort. So you'll have a non-convex corner. So P to Q, that's U, and that's V, and Q to R. Okay. So now you use the fact that your curves do not bound an immersed fishtail, which means that if this goes up, then it cannot intersect itself. Okay, it must come back down. So the other configuration is something of this sort. Okay, so you have, there must be a point in between R and P, let's say Q prime. Okay, so now this bigone is U prime, this is V prime, and now if you just look at, you orient these, you track the degrees, or you track the signs, okay, and the signs just come out from what I just told you, so you can ignore the marked point part, but this one has an effect, and so you can see that the signed contributions cancel. Okay, that's something from P to R for you. Okay, so that's the square of the differential is 0. Okay, so that's just to say that you can actually do things pretty concretely over here. You can play around with pictures as much as you want, and you'll find something interesting. Okay, so right, I just forgot to write down what the CF is. So this is generated over Z, it's a Z module, which is generated by intersection points. So P lies in the intersection of gamma 1, gamma 2. Okay. And this is one thing to note, is that when you define the degree of a point, you see the degree of this point is 0 if you consider P to be an intersection point from gamma 1 to gamma 2. Okay. But if you consider it as an intersection point between gamma 2 and gamma 1, this is not symmetric. Okay. So it's a small exercise for you to show that this, so this is just an exercise using the sign of intersection. Okay. So here degree of P as an intersection point between gamma 1, gamma 2 is 0, and this equals 1 as P in CF gamma 2 gamma 1. Okay. All right. So now that this squares to 0, you have a genuine chain complex. You can define the floor cohomology and so on. Okay. All right. So in the analytic case where you consider the symplectic form, you see we consider bigons that are rigid in the sense that you want them. You remember we always wrote we had to have a particular index. Yeah. You only count those bigons, triangles or squares with a specific index. So it's very rigid in that case. Okay. So for us, this also means something, and for us, this just means polygons with convex corners. Okay. And one can show that the count matches in the analytic picture and also the topological picture. Okay, but what's nice with this topological picture is that this model is very intrinsic to the geometry and topology of the surface. Okay, so M2 is again defined as a composition on floor chain complexes, and it's going to counts, or maybe before that I need to say what is, because this in M2 involves 3 Lagrangians. You remember it's supposed to count triangles. So I need to tell you what admissibility means for higher composition. Or maybe for more Lagrangians or more curves. So that just means something similar, that you have with many curves, you construct a 2 chain. Okay. So that just means that instead of considering 2, you just look at the complement of the curves, the complement inside the surface, you'll get a chain. Okay, you'll get regions in the complement. So you get a 2 chain, and you want it to have Euler measure 0. Comes with positive and negative coefficients. Okay. And so you can define k+1 gons in the usual way, like we defined these oriented immersions, but this time having a Lagrange, having boundary conditions defined on k in k+1 Lagrangians instead of 2, like in the case of bigons. And we check that these mk, they satisfy, again there's a sign involved, but it's just as simple as it can possibly be. It's just a sign and an output. Okay. So this mk just counts oriented immersed k+1 gons with convex corners. Okay. And so you can find, you can define the moduli space, and the dimension of the moduli space is expected dimension, of course, under the transversality assumption, is that this should be equal to k minus 2 plus the index of this k plus 1 gone. Okay, so again this is just k plus 1 minus 3, so up to reparameterizations of by action of the automorphisms group of the disk. And so you have for the differential, you're counting index 1 disks. For for M2, the composition, you're counting triangles. So these are should be of index 0. For M3, you're counting squares, which are of index minus 1, and so on. Okay, and you can check that this satisfies the infinity relation. So where does this admissibility come into play? So admissibility is required for the following. So maybe I can erase this part and show you a picture where you could have in this count infinitely many squares. So if I take two curves that bound a cylinder, and I take two curves which give me this square, which is u, but then I could wrap this around infinitely many times this direction or that direction. What that means is that I could take this cylinder, V is the cylinder bounded by the curves. I could take u plus k times V. So k is any integer, this direction or that direction. So when you take this, you're wrapping around however many times, and you keep getting another square, and then another square, and so on. Okay, so this is what you need to block with admissibility, so you do not allow this to happen. Okay, so these are well defined, you can count these, and that gives you the infinity structure. Okay. So again, this is, as in the general case, not an honest infinity category. You cannot speak of morphisms between a curve and itself, because it's not transversal to itself, it doesn't intersect transversally. So what we do in the, what we can say is something about quasi units, and so we cannot say about units, but we can say something about quasi units, and the result is the following. Okay, maybe I can skip this for now, but maybe leave that as a remark that we do not have units strictly speaking. Okay, so we've basically defined in the topological model the Fukaya category, and now we can do some things like we can compute the growth in D group, but for that we need to have enlarged the category, so it has some sort of a triangulated structure, and I haven't really told you what a triangulated category is, so on and so forth, but you can imagine, just very loosely speaking, that it's an enriched category which admits more structure. And when you have more structure, you can say, for instance, compute this invariant, which is the growth in D group, And in this very, very simple case, it turns out to be as simple as one expects. It's the first homology group of the sphere bundle over sigma. Something it's very light and easy. So that's not what I want to talk about, but however, I could, in the last maybe couple of minutes, I could talk about the action of mapping class group. So the mapping class group of the surface, it acts on the Fukaya category. So it acts by sending sigma to itself, and so by way of sending sigma to itself, it sends the curves to a curve to another curve in sigma, and so so f in the mapping class group acts on curves in the usual way, but I need to say how it maps on the morphisms, which are the floor chain complexes, and at the level or at the cohomological level of floor cohomology, it acts on, let's say, HF of alpha beta, two curves, admissible curves, is defined as HF of F alpha beta. Okay, so you move one of them and then you compute the floor cohomology. Okay, and it's so it's a well-known fact that the dimension of HF equals the geometric intersection number between two curves. Okay, so what is this? This is the minimal intersection between two isotopic representatives of each alpha and beta. So you could look at isotopic curves, which are, so isotopic curve to alpha and isotopic curve to beta, which minimally intersect. Okay, so what this means is that you could have something of this sort, which is two curves. Let me draw them with a yellow. That intersect like this. Okay, so you have 1, 2, 3, 4 intersections. Okay, but you could isotope them, like bring this back. That would get rid of these two intersection points, and then bring this to the left. That would get rid of no. So when you bring it back, you turn it into this blue curve. Okay, so there are these two intersections are not there, but you cannot get rid of these two because they're essential ones, and because of the admissibility condition, you cannot get rid of these two. Okay, so the minimal intersection of these two curves, of two homologous curves, which is the case, is 2. Okay, so that's just to give you an example. So that's a well-known fact, and using this you can actually do some computations, and the result is the following. I'll just write down the result, and maybe you can look at some just to give this a closure. So in general, some sort of automorphism or action of symplectomorphisms on the Fukaya category is in general a subject which people are very interested in. And then eventually what they want to know is how the resulting Fukaya categories relate to each other. So actions on Fukaya categories are very well researched subject. And so it's kind of interesting, but in this case it's really very simple. So there's one thing that I want to tell you is that so if alpha and beta have disjoint representatives, then so they're not isotopic and they have disjoint representatives, then you can show that the Floer cohomology is trivial. Okay, in fact, so let me write it like this. It's an if and only if, and it's a small exercise for you to just think about. It's very easy. It just has to do with a computation of two curves that are not isotopic to each other, which have disjoint representatives, give you as right. Okay, and then we have the following. So HF for an admissible pair, HF of f of gamma 1, gamma 2. So this is the cohomology, Floer cohomology of this pair which has been acted upon by a mapping class. This equals, so if it equals the Floer cohomology of the pair itself, then you can say something about the action of mapping class on the curve and its relation to the curve itself. So this is isotopic, must be isotopic to gamma 1. Okay. So if this holds true for some mapping class f, then f of gamma 1 must be isotopic. So yeah, so this statement, however, does not hold true for separating curves, but nevertheless we have this theorem which says that HF, so if f is a mapping class and this isomorphism holds, so HF of f gamma 1, gamma 2, f of gamma 1 and gamma 2 is isomorphic to HF of gamma 1, gamma 2, then f is isotopic to identity in the mapping class group. So what this says is that the action is faithful on homomorphisms, on morphisms. Okay, so anyway, so the proof is easy. It's quite readable, and it uses the so-called Alexander trick. So you just cut the surface along some generators of the mapping class group such that you can bring it down to a union of disks, and the mapping class group of the disk is trivial. So if you have such a situation, then you can bring it down to identity. Okay, so but this is just to tell you that in this very easy thing you can actually look at things such as the action of the mapping class group, because you have an understanding of the mapping class group of the surface so well, and since this is just a topological model, it's very intrinsic to the topology of the surface. Okay, so I think we can stop here. So we've basically come to appreciate, hopefully, the A side of the homological mirror symmetry conjecture in a very like down to earth example of the Fukaya category of surfaces of genus 2, but in the from a topological viewpoint, completely disregarding the symplectic form. So which means that we're slipping a lot of technicalities under the rug, and because we don't need them anymore. And so we don't need those choices involved. However, there is one harmless kind of generic condition of admissibility which does the trick in this case. Okay, so that's all.